Now we continue class with sample problem number 3, and this time we will be determining the relative volatility for benzene toluene system at two different temperatures. So it's very easy actually. All you have to do is go back to the table that I did show to you a while ago and retrieve the value of the partial pressures of benzene and toluene at the indicated temperature of 90 and 100 degrees Celsius. Now, the next step would be for you to use the formula for relative volatility. So, if it's relative volatility at 90 degrees Celsius for benzene with respect to toluene, in that particular order, then you are to take the ratio of the partial pressure of benzene, rather the vapor pressure of benzene over the vapor pressure of toluene. These two have values equal to 135.5 and 54 taken from the table. And readily, you will have this answer of 2.51. Now, on a different temperature at 100 degrees Celsius, you do the same thing. You read from the table the vapor pressure of benzene and toluene at 100 degrees Celsius and take the ratio of. And you're getting an answer of 2.41. Relative volatility is also temperature dependent, if you notice, because the values varied. So they varied, they are not equal. So relative volatility, if we will say, is temperature dependent. Now the next question is, what would happen if we interchange toluene and benzene here? So it really will matter as well. So if we are asked to determine relative volatility of toluene, so it should be T here with respect to benzene, you also interchange the manner you divide the vapor pressures in here. Now, one very important thing that you should remember with respect to the concept of relative volatility is this, that whenever the values of these two for a system is greater than 1, then at the indicated temperature, separation for such a system is possible. If the value that you are getting for relative volatility at a given temperature is less than 1, then separation is not possible at that indicated temperature. So this one is a very simple illustration of how we make use of vapor pressures to get the relative volatility of a two-component system. Now, our last sample problem requires for you to determine the vapor and liquid compositions of benzene and toluene. The vapor and liquid compositions. Now, in here, if it's vapor composition, we represent it as Y. And if it's liquid composition, we represent it as X. Now, in solving this problem, you need to go back to Dalton's law of partial pressures. And from chemistry 1, it says that the total pressure of your system is equal to the sum of the partial pressures of the component gases. So in this case, our A is benzene, our B is toluene. Now, if this is our first line, if this is our starting point, we make use of Dalton's law of partial pressure. On the next line, we are now using Henry's law to, in this case, we are using not Henry's law, but Rayleig's law in representing the two partial pressures. Now, why did I use Rayleig's law here? It's because we know already that benzene and toluene is an ideal system. So we are allowed to use Rayleig's law. And Rayleig's law says that the partial pressure of a gas above the mixture is equal to the product of its pure vapor pressure and its small fraction in the liquid phase. So I replace the two partial pressures here with its equivalent in Rayleig's law. Then I substituted the pure vapor pressure of benzene and toluene at the indicated temperature of 85 degrees Celsius taken from the table that was shown to you a while ago. So these are the two vapor pressures. Now, if you look at this formula, rather this equation, it has two unknowns. So there's a need for us to express one unknown in terms of another. And oftentimes, we determine the composition of benzene. So if we have a two-component mixture, the sum of the mole fractions in the liquid and in the gas phases are equal to 1 always. It's always equal to 1. So we can say that XB here, the mole fraction of toluene in the liquid phase, is just 1 minus XA. Now we have an equation which has only one unknown, and that's XA. So now we know the composition of benzene in the liquid phase. Knowing the composition of benzene in the liquid phase, all you have to do is subtract this from 1 and you will get the composition of toluene, and that would be 0.22. Now knowing XA is not enough, because here in the problem you are also asked for the vapor composition. So where will we get the formula to determine the vapor composition? And this formula is taken from the very fundamental formula you've learned in chemistry, that the mole fraction of A in the gas phase is equal to its partial pressure divided by the total pressure of the system. The partial pressure again of A, using Rayleigh's law, is equal to its vapor pressure times its mole fraction in the liquid phase. And then we divide that by the total pressure of the system. So if you do the mathematics here, your final answer for the mole fraction of benzene in the gas phase would be 0.9. It follows that the mole fraction of toluene in the gas phase would be 0.10, because we are subtracting 0.9 from 1. So that would give you 0.10. So that would be now the composition of your vapor and liquid in the system benzene and toluene at the indicated temperature of 85 degrees Celsius. Now, phase equilibria of different processes, later on we will look into these different processes one by one. And just to give you an overview, when we speak of gas-liquid equilibria, we will be talking about this in adsorption, in desorption or stripping, and in distillation. So in absorption, desorption, and stripping, and distillation, we will be using gas-liquid equilibria. Now in liquid-liquid extraction, we will be using liquid-liquid equilibria. So the phases that will be contacted are all liquid in this case. Now if it's liquid-solid equilibria, that will be the case of leaching. Okay? And for the case of gas-solid equilibria, that would be adsorption. So the first one is absorption, this one is adsorption. So I think this is the end already of our topic, which is phase equilibria, a primary fundamental principle needed in separation processes. So our next lesson will be about gas absorption, stripping, or shall we say gas-liquid equilibria. Should you have any questions, feel free to drop me a line in my email or in our chat box or in our group chat, and even through Messenger. Thank you for listening.